Good morning, everyone. First, my name is Dr. Yiannis Proestos. Currently, I'm the Data Mining and Information Extraction Leader at the WRF-Chem Center of Excellence for Big Data Analytics. And today, we are very delighted to welcome to you to this invited talk by Dr. Yiannis Proestos. His presentation today is titled Climate Change Impacts, Projections of Heat-Related Mortality in the MENA region and the Global Health Burden of Accelerating Effects on Non-Optical Temperature Compared to the Air Pollution. Dr. Proestos is a computational support scientist and managing director leader at the Modeling and Data Analytics Tool Group at the Cyprus Institute Climate and Atmosphere Research Center, KRCIM. He's also a leading expert in using advanced computational methods to understand complex relationships between climate change and human health. His current work is crucial in assessing the impacts of changing temperature and environmental factors, particularly in regions like the MENA region. Dr. Proestos holds a Ph.D. in theoretical physics, and his expertise spans from high-performance computing, climate modeling, and the analytics of large climate datasets. Currently, as a reminder, Dr. Proestos talk will last approximately 45 minutes, and then we're going to record, as I mentioned, this presentation for later viewing. And then kindly requested that you turn off your cameras and microphones in order to ensure a smooth recording process. Thank you very much, and we'll proceed with Dr. Proestos' presentation. Yannick, you can share your screen and start the presentation.
Yes, Harry. Thank you, and hello to everyone. Let me share the screen. Okay.
It's very good. Thank you very much.
Yeah, welcome and good afternoon, everyone. Today, I'll present our findings of how climate change affects heat-related mortality in the MENA region and compare temperature-related health impacts against air pollution at global scales. Here is the talk outline. First, I'll briefly cover fundamental concepts of climate change. Then we'll dive into the MENA region's heat-related mortality assessment, examine global impacts of non-optimal temperatures and air pollution, and conclude with key messages and future outlook. Let's define what we mean by climate and climate change. Climate refers to average weather conditions over a long period, while climate change involves shifts in temperature, precipitation, and other climate system components. These shifts are driven by both natural processes and human activities, and they have wide-ranging impacts on ecosystems and societies. So how climate is changing, here is an example. So we have a previous climate state and a new climate state. So this graph shows an example of how climate change affects mean temperatures and climate variability. The new climate has shifted to the right, meaning higher average temperatures. The shift to the right, as well as the broadening of the distribution, leads to more extreme weather events, as seen by the increased area under the red portion of the curve, representing extreme weather heat events in this case. So on the right panel here, the first curve corresponds to year 1964 temperature anomaly in distribution. And we know that by 2000, and we know that by 2000, the peak has shifted to higher temperatures to the right, and the curve has started broadening up, suggesting a tendency for increased climate variability. So in 2000 14, the curve at the bottom, indicates even more warming and more variability, that is, more frequent extreme weather events. In this slide, I want to highlight the latest and most concerning evidence of climate change using recently publicized information from the Copernicus Climate Change Service. For the first time, global temperatures in 2024 are exceeding the 1.5 degree limit above pre-industrial levels for several months. This threshold is significant because it is the key limit set by the 2015 Paris Agreement, where nearly 200 countries committed to keeping global warming well below 2 degrees Celsius, with efforts to constrain it to 1.5 degrees. Unfortunately, 2024 ended above this limit at 1.6 degrees Celsius above the pre-industrial level. So how climate change impacts both our environment and human health? Climate change is more than just rising temperatures. It sets off a chain reaction of effects that touch every aspect of our lives. This infographic visually summarizes the direct and the indirect climate change impacts, starting from environmental changes and leading to serious health consequences. The four key climate change drivers are the rising temperatures, air quality, extreme weather, and vector-borne diseases. For example, rising temperatures bring more frequent heat waves that can lead to heat-related illnesses such as heat strokes. As an illustration, this slide shows an example of weather-related fatalities in the USA, emphasizing how these impacts manifest in real-world data. The figures highlight how extreme weather events significantly impact public safety. And one key takeaway from these graphs is the alarming rise in heat-related deaths. Other hazards, such as flooding, tornadoes, and wind-related events, also continue to pose significant risks. These numbers emphasize the urgent need for better preparedness, adaptation strategies, and climate action to mitigate the increasing dangers posed by extreme weather. During the first part of the presentation, I will stand on an urgent but understudied issue: the public health impacts of climate change in the Middle East and North African domain. We aim to quantify how rising temperatures already affect mortality and project future impacts under different emissions and socioeconomic future pathways. MENA countries face a mix of environmental, demographic, and political challenges that compound heat stress risks. Despite its importance, heat-related health outcomes are not well understood due to limited epidemiological data. Addressing this knowledge gap is crucial for effective policy and adaptation. For our study, we divided the MENA region into 4 sub-regions based on climate similarities, drawing on previous research. Each sub-region's heat mortality relationship was estimated using established temperature mortality exposure risk parameters, helping us capture the regional differences in vulnerability. The analysis briefly combines data from 10 CMIP6 climate models that were statistically downscaled and bias adjusted across multiple IPCC shared socioeconomic pathway scenarios. And our analysis covers 19 states over the MENA domain. So this slide summarizes our methodology briefly to quantifying heat attributable mortality in the MENA region. We calculate heat-related mortality using a transfer function which accounts for projected population changes, baseline mortality rates, and heat exposure response coefficients. The key component here is delta T, which represents the key climate component here is delta T, which represents the apparent temperature exceedance beyond the climatological 95th percentile. The apparent temperature, considered as a heat stress metric, incorporates both temperature and relative humidity effects. Through the combination of climate and demographic projections, we can estimate annual heat-related deaths across different timescales and scenarios. So this slide presents the climate variables. Here we have the mean annual temperature anomaly. So we see the evolution of the climate model ensemble mean annual temperature anomalies across the 4 MENA sub-regions we selected. The historical period spanning years from 1980 to 2014 is represented with the black line, while future projections follow different SSP pathways for years 2015 until the end of the century. Notably, SSP5, which is, by the way, the pessimistic scenario, the high emission scenario, shows the most extreme warming with temperature anomalies reaching up to 8 degrees Celsius by the end of the century in G in sub-region C. Even intermediate scenarios, like SSP2, indicate significant warming, which is above the 2 degrees Celsius threshold, emphasizing the urgent need for adaptation measures. Also, this climate information serves as the foundation for estimating future heat attributable mortality across the region. Here, the slide presents the population projections for the MENA region under the 4 SSP scenarios. So here we use data from NASA's SETAC dataset to estimate the annual population changes from 2000 until the end of the century using year 2000 as our baseline population. Additionally, we incorporated all-cause mortality projections from the UN World Population Division to refine our projections. So we see that the SSP3, which is a high emission scenario as well, represents the most rapid and continuous population growth, especially for region C, while SSP1 and SSP5 suggest slower growth with a peak followed by a drop. SSP2, which is the intermediate scenario, stabilizes toward the end of the century as expected. Also for SSP3, we know that it projects population growth exceeding 300 million people in region C and above 250 million people in region D, significantly increasing the potential for climate-related health burdens. These demographic projections are critical for understanding how population dynamics interact with climate stressors and play a key role in the projections of heat-related mortality in the region. So here is the projected spatial distribution of the annual mean climate anomalies, focusing on temperature and relative humidity, which are used to estimate the apparent temperature. So here we see the temperature. The first column corresponds to the SSP1 scenario, and so on. And the first row corresponds to the first 20-year period between 2021 and 2040, and so on. It is evident that under high emission scenarios, SSP3 and SSP5, the region warms significantly by 2060, with the strongest anomalies in North Africa and the Arabian Peninsula. In fact, the warming is more pronounced when examining the summer months, June, July, August, with temperature anomalies exceeding 6 degrees Celsius in extreme scenarios. Also, some coastal areas around the Arabian Peninsula show elevated relative humidity, suggesting intensification of heat stress. So these projections emphasize the urgent need for regional adaptation strategies, especially in heat-exposed and densely populated areas. This slide summarizes the baseline heat-related mortality risk across the MENA region during the first 20 years of the 21st century. The map shows the annual mean heat-related mortality rate per 100,000 people, with darker colors indicating lower mortality rates and brighter colors representing higher risks. Key findings indicate that Egypt bears the highest absolute burden, with about 2,600 heat-related deaths annually. However, when adjusting for population size, Iran emerges as the most vulnerable country, experiencing an estimated 11 deaths per 100,000 people each year. This highlights Iran's higher exposure to extreme temperatures relative to its population size. On average, the annual heat-related mortality rate across MENA was about 2 deaths per 100,000 people, though rates vary significantly by each sub-region. This baseline assessment is critical for understanding how future climate change may further enhance heat-related health risks across the region. So here is the projected future. So it's a summary of the projected changes in heat-related mortality rates across the MENA region under the 4 different scenarios that we selected: SSP1, SSP2, 3, and 5. And for 3 periods: 2041 to 2060, 61 to 80, and 81 until the end of the century. The darker shades indicate more severe increases, with the highest impacts are projected as expected under SSP3 and SSP5. So by the end of the century, heat-related mortality in MENA is expected to rise dramatically, reaching an average of 123 deaths per 100,000 people under the high emission scenario. Even under SSP1, the low emission scenario, mortality rates could still double or triple compared to the baseline period. So the Gulf states emerge as a critical hotspot, with some areas projected to experience extreme increases in heat-related deaths. Notably, Saudi Arabia could see a 13-fold increase in mortality rates under SSP1, but in high emissions future SSP5, this could surge up to a 63-fold increase. So these projections underscore the urgent need for mitigation strategies, heat adaptation policies, and climate resilient infrastructure to protect vulnerable populations from escalating heat-related health risks. Also, a key driver in the heat-related mortality increase is population growth. Even when we consider the population constant throughout the century, mortality still rises significantly due to climate change. However, when population variation is included, the increase is even more dramatic, particularly under SSP3, which projects strong population growth in highly heat-exposed regions. So this analysis underscores the double challenge of climate change and demographic shifts in shaping future heat-related mortality in the MENA domain. So here we see temporal trends in projected heat-related mortality for the MENA countries considered in the study. The plots are arranged by increasing mortality impact, with low burden countries at the top and high burden ones at the bottom. And the color curves represent different SSP scenarios, while the shaded areas reflect the climate model uncertainty, which increases over time as climate variability and population projections become less predictable. Looking at the results, before mid-century, trends across scenarios look similar, but diverge sharply after 2050. Also, regional variability is striking. For example, Iran is projected to have the highest mortality rates, potentially above 400 deaths per 100,000 people by the end of the century. Palestine also faces steep increases tied to rapid population growth. Summing up, this is the first region-wide assessment of heat-related mortality in the MENA domain. We estimate future burdens for countries lacking robust epidemiological data and highlight how population growth strongly influences future mortality burdens, ultimately limiting warming to around 2 degrees Celsius could avert a 6-fold increase in heat attributable deaths compared to a high emissions future. Now let's continue to the last part where we present the global and regional impacts of atmospheric health burden associated to non-optimal temperature and air pollution. So climate change and air pollution are two of the most significant environmental health risks. This work builds on the global burden of disease study, which attributes about 6.5 million deaths annually to these dual risk factors, with PM2.5 accounting for about 90% of air pollution-related mortality. Our primary objectives are to estimate the current and future global mortality attributable to non-optimal temperature and PM2.5 exposure, and to compare these risks under different climate change scenarios using CMIP6 models and SSPs as in Part A. We also aimed at assessing the role of population growth and aging in these trends. So this slide briefly outlines the data and methods adopted for this study. Namely, we used 3 of them bias-adjusted CMIP6 climate models used in Part A, since only those 3 models included the PM2.5 air pollution data. And we limited the projections, the future projections, to 3 climate change scenarios: SSP1, the optimistic scenario, the intermediate, the SSP2, and the pessimistic SSP5. We also used baseline mortality rates extracted from the Institute for Health Metrics and Evaluation of the University of Washington. We used also age-distributed population data from applied system analysis. And the exposure response functions we used to calculate the attributable mortality for non-optimal temperatures and PM2.5 were also derived from the global burden of disease study of 2019. This is just a brief. Let's focus on the global mortality attributable to non-optimal temperature and air pollution for the period between 1990 to 2010. I will call it period 2000. It's the average, basically. So this is the spatial distribution of the global mortality attributable to atmospheric factors and it was about 5.7 million, with 28% due to non-optimal temperature and 72% due to air pollution. And we see that South and East Asia bore the highest burden, reflecting both high pollution levels and also large populations. So in these projected temporal mortality plots, we see that by the end of the century, global mortality attributed to both environmental risk factors is projected to increase dramatically. Under the intermediate scenario, we estimate around 30.3 million deaths, while under the SSP1 and SSP5, we project 36.9 and 44.3 million deaths, respectively. So the following 3 slides that will be presented and depict the global distribution of the mortality changes, contrasting the end of the century period to the beginning of the century. And we start with the low emissions scenario. So here we see that regional trends show that South and East Asia will continue to experience the highest mortality rates. However, temperature-related mortality is projected to increase globally. So it's everywhere red. While pollution-related mortality may stabilize or decrease in some regions, likely due to emission reductions. Similarly, for the SSP2 scenario, and SSP5, which is the high emission scenario, we see that the increases relative to the baseline period are more pronounced here for both risk factors as expected. Nonetheless, in many places, exposure to these 2 risk factors will have compounding consequences. So we see that temperature-related mortality is projected to increase by 6.7 to 10.9 times by the end of the century, compared to 4.8 to 6.6 fold increase for air pollution relative to 2000. So this shift means that non-optimal temperature will become a more significant risk factor than air pollution in many regions, highlighting the growing impact of heat stress as global temperatures climb and emphasizing the need for climate adaptation strategies. Here is a table with, which summarizes the results for different regions around the globe. Now let's discuss the key factors influencing mortality across century. First, population growth plays a significant role. So here is the population. The global population is projected to peak at around 9.3 billion people in 2070 under the SSP2 intermediate scenario. This growth increases the number of people exposed to both non-optimal temperatures and air pollution. Second, population aging is a critical driver. The average age of the global population is expected to rise steadily from 32 years in 2010 to between 46 to 56 years by the end of the century. So older populations are more vulnerable to the health impacts of temperature extremes and air pollution, leading to higher mortality rates. This is more pronounced in the optimistic scenario, for example, SSP1. Finally, exposure to temperature and pollution is shifting. According to this plot, globally, population-weighted temperature exposure is projected to increase from 19 degrees Celsius in 2000 to 22 up to 24 degrees Celsius by the end of the century, depending on the future pathway scenario. Meanwhile, PM2.5 exposure is expected to peak between 2010 and 2040, before declining due to air quality improvements in some areas. These factors, population growth, aging, and changing exposure levels, are the primary drivers of the projected increase in mortality attributable to atmospheric factors. So here we have a country level mortality. We have the country level mortality rates per million people due to long-term exposures. And we start with the SSP1. So in 2000, we see that the highest temperature-related mortality occurred in northern latitudes, including Russia and Canada, as shown on this panel. Similarly, in panel B, highlights the air pollution mortality burden, particularly in Eastern Europe and Asia. By the end of the century, under this scenario, panel C shows that temperature-related mortality is projected to increase significantly over the entire globe, mainly due to the projected population aging aspect under this scenario, as we mentioned before. The largest increases are expected in tropical regions, Latin America, as well as in the MENA domain. So in this panel, panel D, we see an increase in PM2.5 related mortality, particularly in Africa, parts of Asia, South America, while in Europe and northern latitudes, we see a decline in mortality. So this is the same, but for SSP2, the intermediate scenario. So here in panel C, we see a less pronounced increase in temperature-related mortality compared to the beginning of the century. Note that the rise is milder compared to the previous scenario. This is associated to the aging population effect mentioned previously. And here in the bottom figure, which shows the PM-related mortality, we see that it's declining or stabilizes in most regions, in particular over northern latitudes. However, the MENA region still remains vulnerable to the PM2.5 exposure risk, as the mortality risk is elevated. So here is the business as usual scenario, the high emission scenario. The future projections in this pessimistic scenario are particularly alarming. So here in panel C, we see a dramatic increase in temperature-related mortality across the globe, especially in South America, Africa, and Asia. The mortality burden is much higher than in the previous two scenarios due to extreme ongoing warming. Similarly, in the last panel, panel D, shows the PM2.5 related mortality increases also significantly, particularly in Africa, the Middle East, and parts of Asia, reflecting severe air pollution impacts, while for northern latitudes, the mortality has declining trend. So here, the following slides compare the two components of the non-optimal temperature, the warm and cold-related deaths per decade, starting from 2000 until the end of the century. So warm temperature-related mortality is projected to increase by 23 to 52 times by the end of the century, compared to 5 to 7-fold increase for cold temperatures. in absolute numbers, the cold weather-related deaths are significantly higher in this case than those related to hot weather conditions. So this is SSP1. Similarly, we see a similar pattern for the intermediate scenario. Here we see for the temperature an increase of 22-fold and for warm temperatures, and for cold temperatures we see an increase of 5-fold. So under the business as usual scenario, the result for this one is pessimistic, and so it's up to a 52-fold increase in warm-related deaths and about 6-fold rise in cold-related deaths by the end of the century compared to the beginning of the century. In all of these scenarios, warm temperature mortality rises more sharply than cold-related mortality, which also increases, but at a lower rate. Overall, this scenario exhibits the largest growth in heat-related deaths, and we see that by the end of the century, the absolute number of deaths are becoming similar for both warm and cold weather conditions. This slide depicts the results for the spatial distribution of the changes in mortality due to exposure in cold and warm temperatures. So it's the end of the century versus the beginning of the century. We know that population growth and aging offset the reduction in cold temperature mortality due to rising global temperatures. Climate change not only increases average temperatures, but also enhances temperature variability, potentially leading to more frequent extreme weather events. For example, this could potentially lead to extended cold waves in some areas. These changes amplify health risks, particularly for vulnerable populations, highlighting once again the need for robust adaptation and mitigation strategies. So areas in the tropical zone, such as Sub-Saharan Africa and South Asia, as well as MENA, will experience the largest increases, exacerbating existing health disparities. So here is the synopsis. Our results align with previous studies suggesting lower end estimates despite our assumption of constant baseline mortality rates. In conclusion, our study shows that temperature-related mortality will surpass pollution-related mortality in many regions by the end of the century. Climate change poses a direct threat to human life expectancy, and stronger climate policies are urgently needed to prevent future loss of life. Our findings underscore the need for integrated climate and air quality policies with a focus on adaptation strategies for vulnerable populations. So here, global cooperation is essential to reduce emissions and mitigate the health impacts of climate change. And looking ahead, we plan to spatially downscale and bias adjust global high-resolution simulation output using machine learning methods, leveraging data from the EMAC atmospheric chemistry general circulation model forced by SSP scenarios. This will enable more accurate climate change impact studies focusing on vulnerable regions. Additionally, we aim to investigate the synergistic effects of temperature and air pollution, including near-surface ozone, to refine our understanding of future atmospheric health risks. Finally, the presented work is the result of international joint efforts, and here are the two references where you can look for more technical details. Thank you so much for your attention.